Hi, good day. For today, I'll be giving you the next module, which is all about the higher order linear differential equations. In this module, we will discuss the definitions and forms of higher order linear differential equation. We will also have discussions on how to determine whether function is linearly independent with each other. The concept of the differential operator will also be introduced in this chapter. For the topic outcomes, at the end of this module, you should be able to recognize the general linear equation and identify its order and homogeneity by writing a differential equation into the general linear form. Recognize the linear independence of functions correctly by solving its Wronskian determinant. Determine the general solution of linear DEs. Write a DE using the differential operator form correctly and vice versa. And distinguish the operations applicable to the differential operator by performing them to the differential operator. Now, what is the general linear differential equation? The general linear differential equation of order n can be written in the form as presented in equation number 1. BO as a function of x, the n derivative of y with respect to x, plus B1 of x, the n minus 1 derivative of y with respect to x, plus up to Bn minus 1 of x, the first derivative of y with respect to x, plus Bn of x times y is equal to r of x. If the value of r of x is 0 for all values of x, then the equation is homogeneous differential equation. If r of x is not 0, then that is said to be non-homogeneous differential equation. A linear differential equation has constant coefficients if all coefficients bi of x are constant. If one or more of these coefficients is not constant, then meaning it has variable coefficients. If the coefficients bi of x and the function r of x on the right side of the equation are continuous on the interval I, and bo of x is never 0 on I, then that said general linear differential equation is normal on that particular interval. Now let us have the following examples. Let us identify the order, linearity, and homogeneity of the differential equation and the interval in which the equation is normal. So for problem number 1, you have x plus 1 times y prime plus v is equal to cosine of x. If we are going to look on the highest order derivative, we have here the first derivative. So it means this is first order. And then, since the right side of the equation is equal to cosine x, which is not equal to 0, then this is said to be non-homogeneous. And then in terms of linearity, if we check our requirements, you have y as your dependent variable. So you have x dy, and you have here cosine x. So none of the requirements is violated. So therefore, the first equation is said to be linear. So again, that is first order, linear, and non-homogeneous. Then what about the second sample problem? 3 times the second derivative of y with respect to x plus xy is equal to 0. So the highest order is the second derivative. So this is a second order ordinary differential equation. This is linear since none of the three items were violated. And then this is homogeneous because the right side of the equation is 0. Now we go to determining the interval in which the equation is normal. As mentioned in the previous slide, it is said to be normal if BO of x is not 0. So for number 1, x plus 1 is our BO. So therefore, this will be normal if x plus 1 should not be equal to 0. Or meaning, if x is not equal to negative 1. Because if x is negative 1, this BO will become 0. For number 2, we have here the value 3. So it is normal on any interval because it will not be 0 anymore. Okay? Theorem number 1. Any linear combination of solutions of a homogeneous linear differential equation is also a solution to the equation. This is actually the theorem of superposition. Assuming an nth-order linear homogeneous differential equation given by equation number 2, again, if it is homogeneous if the right side of the equation or our r of x in our equation number 1 as presented in the previous slide is equal to 0. It has a solution y1 and y2 if c1 and c2 are constants. Therefore, our solution by principle of superposition is y is equal to c1 y1 plus c2 y2. Similarly, it can be seen that if yi with I equals 1, 2 up to k are solutions of equation number 2, and if ci with I equals 1, 2 up to k are constants, then y equals c1 y1 plus c2 y2 plus up to ck yk is also a solution of equation number 2, which is again linear homogeneous differential equation. So in the next module, we will be dealing more with the solution of this linear homogeneous differential equation. Theorem number 2, given an nth-order linear differential equation. Now this time, we will see here that the right side is r of x. So this is actually a non-homogeneous linear differential equation. If that is normal on the interval I, suppose that xo is any number on the interval I and yo, y1 up to yn minus 1 are n arbitrary real numbers, then a unique function y is equal to y of x exists such that y is a solution of the differential equation on the interval and y satisfies the following initial conditions. That y at x equals xo is yo, y prime at x equals xo is y1, up to yn minus 1 of xo is equal to yn minus 1. So in module number 6, we will be dealing more of the solution of non-homogeneous linear differential equation. Now we go to linear independence. What is this linear independence? We want actually to determine whether the given functions are linearly independent or not with each other. So given the functions f1, f2 up to fn, and if the constant C1, C2 up to Cn not all zero exists, such that C1 F1 of x plus C2 F2 of x plus up to Cn Fn of x is equal to 0. For all the values of x in some interval, x is greater than or equal to a but less than or equal to b, then the functions f1, f2 up to fn are said to be linearly dependent on that interval. If no such relation exists, the functions are said to be linearly independent. That is, the functions f1, f2 up to fn are linearly independent on an interval when the equation number 1 implies that C1 equals C2 equals Cn equals 0. It should be clear that if a function of a set is linearly dependent, at least one of them is a linear combination of the others. If they are linearly independent, then none of them is a linear combination of the others. Now we go to Wronskian. With the definition of linear independence, we shall now obtain a sufficient condition that n functions be linearly independent on the interval x greater than or equal to a but less than or equal to b. Let us assume that each of the functions is differentiable at least n minus 1 times in that particular interval. Then, that given equation of C1 F1 of x plus C2 F2 of x up to Cn Fn of x is equal to 0. It follows by successive differentiation. If you take the derivative of all the functions, then you have on the first differentiation C1 F prime of x plus C2 F2 prime of x plus up to Cn Fn prime of x. Then the next would be the second derivative, and the last would be the n minus 1 derivative of the function. The number of differentiation actually depends on the number of the functions. So if you have 3 functions given, then the last one should be the second derivative. For any fixed value of x in that particular interval, so the nature of the solution of this n-linear equation will be determined by the value of the so-called Wronskian determinant, or we represent it as W. So if W is not equal to 0 for some XO on the interval, then it follows that C1, C2 up to Cn, and hence the functions are linearly independent. Take note again, if the value of the Wronskian determinant is not equal to 0, then the functions are said to be linearly independent on that particular interval. So how do we find the Wronskian determinant? So the equations presented on the previous slide will be put into determinant form or in this matrix form, and then we obtain its determinant. Again, W is Wronskian determinant, which was named after Wronski.